Hello everybody. What this lesson is going to be addressing is kind of the culmination of everything that we have been working for in prior lessons about solving either a log or an exponential equation. You kind of need to know something about both of them in order to solve certain types of equations. The types of equations that we're going to be looking at here are going to start off in exponential form, but they're not going to give us a common base for us to be able to try and simplify to, which means that we're going to have to do something with logarithms. And I'm not trying to scare anybody off here, but these are going to be slightly more complicated than other problems that we have taken a look at. So looking at the steps that we have here on the screen, if we can't identify a common base between the two exponents that we have, what we'll do is we'll just take the log of both sides of the equal sign. Because generally speaking, a lot of times what we're working for in this problem, or in these types of problems, is x, obviously, or some variable, but unfortunately it's going to be in the exponent's position. That's what makes it an exponential equation. And by converting it into a log, what we're going to do is we're going to be able to use properties of logarithms to take the variable from the exponent spot and take it out of there. So that way we can actually do some things with it. Now, number two, that step right there is talking about the power rule. Okay, well that power rule says, okay, well we have, let me get my pen turned back on. It doesn't like it when I do other things with it. So let's say we have, I don't know, log of uh, log base 10 of b to the x plus 4 power. Well, the power rule of the logarithm says, well, we can take that exponent and move it down, which we would say x plus 4 times the log of b. And we've seen that in previous lessons, and that was the extent of what we needed to do to demonstrate the power rule. Now, step 3 says distribute if necessary. Well, what that means is that I can take whatever number the b is and distribute it into the parentheses. So I have log of b multiplied to x, so that'll give me x times log of b plus 4 times log of b. That's kind of what it's talking about there when it says distribute if necessary. And that green looks rather thick for some reason. I don't know why it seems so thick. I'll try a different color here. I don't like it when it's so thick. But anyway, I'm getting off on a tangent. So that is what step 3 is saying. It says, okay, well, distribute if necessary, so that's what we would do. And step 4, it says move your x's to one side of the equal sign. And that is usually where we actually run into problems, is in step 4, because that is a bulk of where the algebra comes from, is getting x on one side of the equal sign. And once I do, then we can, in step 5, say, okay, we'll type what we have into our calculator and see what we have for our answer. So here is a very typical type of exponential equation where the earlier simpler equations, we would check to see those rules. Okay, I'd say, well, 3 on the left side is a prime number. And I'd say, well, can I raise 3 to be 427? If I say 3 to some power, will it give me 427? Well, if I say 427 and I divide it with 3, well, that's going to give you 142.333 repeating. So 3 isn't even a factor of 427. So that means we cannot raise 3 to any number to have it equal 427. So it's not possible to get a common base with these exponents. So step 1 said just take the log of both sides. So the way I do that is I'm going to simply say log of 3 to the 5x plus 4 power will be equal to the log of 427. Now, at this point, by converting the exponent into a logarithm, we can take the exponent, the 5x plus 4, and use the power rule and relocate it in front of the logarithm. So that would give me as an expression 5x plus 4 times the log of 3 to be equal to log of 427. And you could, when you convert it, you could use log base 10 or natural log, but my preference personally for some reason is just log instead of natural log. But anyway, at this point now, we could actually do one of two things. Because I only have x on the left side of the equal sign, we could start dividing with the log of 3 and then move the 4 over and divide by 5. But um, what I'm going to do is I want to try and be consistent with the examples that I'm going to show you. And I know if I do it one way for one problem and another way for another problem, then I have a tendency to lose students, and I don't want to do that. So what I'm going to do is I'm going to distribute the log of 3 into the parentheses, and I'm going to get 5 times x times the log of 3 plus 4 times the log of 3 to be equal to log of 427. And we will kind of treat this like a normal equation. Now, I know it doesn't look normal to us, but we have one term on the left, the 5 times x times log of 3, and we're adding another term to it, the 4 times log of 3. And so we will kind of, you know, work our magic, do our order of operations backwards, and I'm going to subtract 4 times the log of 3 from the left side and from the right side, because anything you do to one side, minus 4 times log of 3. So by doing that, they cancel each other out on the left side of the equal sign, so I'm left with 5 times x times the log of 3 to be equal to, now, even though they're the same base of base 10 for the log, they're not like terms, so we can't kind of combine those together. So we just write it as log of 427 minus 4 log of 3. And we're not concerned about trying to condense it or anything like that. That's not what we're trying to do here. We're simply trying to isolate x. Now at this point I'm going to go ahead and I just want to rewrite the problem because I don't want my steps to blend together. So I'm just rewriting what we had originally. So log of 427 minus 4 times the log of 3. Now the 5 and the x and the log of 3, they're all being multiplied on the left side of the equal sign. So if they're all being multiplied on the left side of the equal sign, and I want to get everything away from x, then that means I will divide by the 5 times the log of 3 on the left side, and I will divide everything here by 5 times the log of 3 on the right side as well. So the 5 and the 5 simplify to be 1. The log of 3 and divided by the log of 3 simplify to be 1. And I'm left with x to be equal to log of 427 minus 4 times the log of 3 divided by 5 times the log of 3. Now this is what we would generally think of as an exact answer, where we have x is equal to something. Because you can say log of 427 on your calculator and it'll give you some decimal number. It'll give you some irrational number that never repeats. So we don't want to write the rounded decimal number and then do math with it. We want to do the math like this. Now, what we'll do is you can do it, you can actually type this into your calculator in one keystroke. Just make sure that you keep your parentheses proper. If you type it into the calculator, the very first thing you want to do is put a parenthesis around everything in the numerator. So you start off with a parenthesis here, the log will open up a parenthesis, and then I'll close a parenthesis around the 427. Then I'll say minus 4 log 3, which will open up a parenthesis here, and I'll close it, and ultimately close the parenthesis of the numerator. Then I'll hit the divide by button, and then I'll open up a parenthesis of the denominator because we want to do everything together. And then when I hit the log button, it'll open up a parenthesis on the 3. And then I'll close that one and close the whole denominator. So we type it in like that. You may take a couple of practice keystrokes to make sure you get everything correct. You could always do everything in the numerator, save it in your calculator, do everything in the denominator, save it in your calculator, and then divide the two from each other. But either way, at some point, you should, on your calculator, get x to be, and we're going to round it at this point, approximately 0.3026 for our answer. So there is our first example. So moving on, here, second example. Now this one is pretty straightforward, that two bases in this uh, ex, uh, exponential equation, they definitely don't have a common base because both of them are prime numbers. So they definitely can't be factors of either one. So we will do the exact same thing that we did. The key difference between this example and the previous one is that if you notice in the exponent spot, here we have variables in both positions on the left side and the right side. And so that is primarily why I wanted to use the distribution on the first example, because I have no choice but to use it here in order to isolate my variable. So again, first thing we want to do, convert into a log. So I'm going to say log of 2 to the x plus 3 power is equal to log of 5 to the 2x power. Okay. Now, we do have logs of the same basis here, but we can't just say the 2 to the x plus 3 is equal to the 5 to the 2x power, because we wind up right back where we started. So using the property of the log power, we're going to take the exponents and relocate them in front of the logs. So I will say x plus 3 times the log of 2 is equal to 2x times the log of 5. And in this case, this is where in the last example I said, well, I want to go ahead and keep things consistent. I want to distribute the log on the left side into the parentheses because in this example I know I needed to do that, because if I wanted to work this problem out the way it is, and I tried dividing by the log of 2 on the left side and by 2x on the right side, we will never be able to isolate our variable. It's always going to wind up either on the left side and the right side, or at the top and the bottom on the left side or the right side. So we have no choice but to use that distribution technique on the left side of the equal sign here. So I'm going to get x times the log of 2 plus 3 times the log of 2 to be equal to 2x times the log of 5. So at this point, what I want to do, because I have an x on the left side of the equal sign and an x on the right side of the equal sign, is we want to get them on one side or the other. And if I didn't do that distribution, we wouldn't be able to get them on the same side where they're both on the top of like a fraction. So at this point, what I'm going to do is I'm going to take the x times the log of 2 from the left side and move it to the right side. There's nothing saying I have to do it this way. I just think it'll work out nicer this way, having the negative sign behind something rather than in front of something. So we'll say, and also there's only one thing to move as opposed to two doing it this way. So minus the x times the log of 2. So on the left side of the equal sign, these cancel each other out, and I'm left with 3 times the log of 2 being equal to 2x times the log of 5 minus x times the log of 2. Now, I keep putting the parentheses around the 2x before I say log of 5, and I do that just to show you that, well, the 2 and the x are still being multiplied to the log of 5. I don't need to write the parentheses here, and I think it will be easier to see what I'm going to do if I don't have the parentheses anymore. But what we have is two things that are subtracted from each other that both have x. Because they both have x, we can factor x out of the problem on the right side. So I can take an x out, and I'll be left with 2 times the log of 5 minus the log of 2. By factoring the x out of the two terms on the right side, we can now divide by everything that is in the parentheses, and it will isolate x on the right side of the equal sign for us. So I say 2 times log of 5 minus the log of 2, and I'm going to divide on the other side, same thing, 2 times the, a lot of writing here, unfortunately, because of the fact that we're working with logs, but it's definitely better to write it this way than the rounded decimal numbers. So on the right side, anything divided by itself simplifies to be 1. So now I have 3 times the log of 2 divided by this whole long thing, the 2 times log of 5 minus the log of 2, to be equal to x. And so again, at this point, we would consider this to be an exact answer. And we'll go ahead and kind of bring it up here to show what the value is. So again, type this stuff in the numerator separately, type this stuff in the denominator separately, and then divide them if that's what you need to do to get the keystrokes under control. But when you do, you should get x to be, and at this point we'll round our number, should be approximately 0.8233 for our answer. Okay, and again, if you're having questions at any point as I'm going through, make sure you write them down and bring them to me when you come see me in tutoring or in class. So here is our last example that we're going to work with, and this one is doubly troublesome, probably for some of us, just by looking at it. There's the dreaded fraction on the left side of the equal sign, and it is also containing an exponent. So what do we do? Now, at its most basic, what we have on the left side is just a division problem. We have 80 divided by something. So if we don't like the fraction, we can get rid of the fraction by multiplying everything in the denominator. So I will multiply 1 plus 15 times e to the negative 0.06x power on the left side and on the right side. So 1 plus 15 times e to the negative 0.06x power. So here, this and this would just simplify to be 1, which will leave me 80 is equal to 50 times 1 plus 15 times e to the negative 0.06x power. Well, clearly, if the variable that we're looking for is no longer in the denominator of the fraction, in fact, we have no fraction at all. Everything would be considered in the numerator of a problem at this point. And 50 is multiplied to the expression that has the x, so we want to get rid of anything that is with it. So the easiest thing at this point is to get rid of the, because we definitely don't want to distribute the 50. That would just make things weird. I mean, you could, but it would just give us bigger numbers inside of the parentheses to work with. So let's just go ahead and divide by the 50. Now, 80 over 50, that just simplifies to be 8 over 5. And it'll be nicer to keep it as a fraction rather than a decimal, because that's not going to be, actually, no, it does work out to be a good decimal. You can say 80 over 5 and leave it as 8 over 5, or this will be one of the instances where I think the decimal will be pretty nice to work with. 8 over 5 is just, wait a minute, I'm getting ahead of myself. Yes, I will keep it, because I'm just looking at my notes. I'll just keep it as 8 over 5 for the time being. 8 over 5. And it'll be equal to, so by dividing by the 50, we no longer need to write the parentheses on the right side of the equal sign anymore. And so the next thing logically to do would be to move the 1 over. So if on your calculator, if you say 8 divided by 5 and then subtract 1, that is where you're going to, let me grab a calculator real quick. I don't want to pause the video because I want to start all over, but 8 over 5, yes, is 1.6, and then if I subtract 1 from it, I will get simply 0.6 to be equal to 15 times e to the negative 0.06x power. Okay, now the 15 is multiplied to e. Remember, the base of the exponent is actually e. So at this point, I will divide by 15. And if you say 0.6 divided by 15, that'll still give you a nice, fairly nice decimal. That'll give you 0.04 is equal to, let me clean that up a little bit. 0.04 is equal to e to the negative 0.06x power. Okay, so now at this point, because it is e, we will go ahead and take the natural log of both sides. So if I say the natural log of 0.04 and the natural log of e to the, let's see, where am I at here? Negative 0.06x power. Well, the natural log of e, if you just type that into your calculator, if you say the natural log of e, that just simplifies to be 1. Okay? So what we'll do before we do that is we'll just again take the exponent, use the property of the exponent rule here, and move it in front of the logarithm. So I'll say the natural log of 0.04 is equal to negative 0.06x times the natural log of e. I seem to have some gaps where the camera is picking up missing some parts on the board when I write on it. Okay, so and again, this is where I want to show you that the natural log of e is just 1. So I have the natural log of 0.04 is equal to negative 0.06x, because I'm not going to write the 1 because 1 multiplied by anything doesn't change anything. So finally, I will divide by everything by negative 0.06, so I'll have x is equal to the natural log of 0.04 divided by negative 0.06. And again, that's what we would consider to be our exact number. And so our final rounded approximate number will be about 53.6479. And that's what we're going to be looking at our solution here. So again, just to kind of recap, if you don't have common bases, take the log of both sides as you know, when it's appropriate. The reason why I didn't take the log of both sides at the beginning of this problem was because the variable of our exponent was in the denominator of a fraction, so we had to do some things to get it out of the denominator first. Once you do that, use the rule, the power rule for logarithms to move the exponent down in front of the log, distribute if necessary, and then use your opposite operations of algebra to isolate your variable. So this is going to kind of wrap it up as far as our curriculum's unit on logarithms. As far as log equations, we still have a little bit more to do when it comes to interest and finances and stuff like that. And there's some particular formulas that we'll be practicing with that. But this is pretty much it as far as specifically log equations and properties of logarithms. So again, as you watch the video, make note of any particular concepts or operations that you might have questioned about why did I do something the way I did, and bring that to me when you see me in class or in tutoring next. And thanks for watching, and we'll see you soon.